Hey everyone, welcome back to the shop. I'm Rob, and in this video, time to make possibly the coolest part of the whole build. Got to take the head that we built in the last video and make it move. Gantry carriage time. Alright, first thing to do is to prep up the 60-tooth pulley, get it ready to go into the idler nut assembly for the Z-axis. Just drilling it out, boring it. That's the same mini boring bar that I ground in the last video. Taking it to the exact diameter of the nut shank and then turning out the counter bore for the bearing to go into. Bearings are sized mainly for the 60-tooth pulley, but the inside is not 8mm, it's larger so that you can actually grip it from the inside. If it was just a 8mm through hole, then there would be no way of holding it from the other side in order to actually mount it on the head. That's the finished assembly, ready to go. Now we just need the mounting bracket. Since this is all going to be held together by gravity, I don't need to do any kind of weird clamping mechanism, which is a good thing since I didn't actually leave myself any room for it. The walls of the steel bracket on the inside of the bearing are probably only going to be about 1mm. Everything below that is just clearance. Fairly standard workflow for this, just facing and turning down one side so that it can be held once I flip it around. Obviously with this there's not a whole lot of holding space. I didn't want to have to turn down massive amounts of steel, considering I would only have the tiny little nub that I'm leaving on there left to hold it by. First thing to do is just to get a ballpark for the base plate, make sure I'm getting it about in the right place. Normally I try to leave it a couple thou over so I can do a final skim pass, but because steel itself is overkill for this actual specific part, I wasn't too worried about variances in thickness. The main thing on this is the ID being just over 8mm and the OD of the nub being probably about 2 thou less, maybe a 20th of a millimeter. It's 50 microns less than the ID of the bearing. I want a comfortable push fit where you push it in and it doesn't move, but I don't need it to be a press fit. I'm making a 6-hole bolt pattern here. I don't think I'll actually end up using all 6, probably just 3, and then use the screw heads on top to offset the inner race of the bearing up off of the flange there. As you can see, it assembles quite nicely. I don't know if I'm always going to use those grub screws to hold the brass nut, or if I'm actually going to drill and tap the pulley in order to actually screw it down. There's nothing going to be on top of it to prevent that, so depends how concentric the nut is, I guess. We'll see in practice. Just stopping the screw from rotating with my little finger there, allowing it to rack in and out as I rotate the pulley. That's actually how an industrial linear actuator works. In fact, now I'm thinking about it, that's exactly what I'm building here. The same offset motor to a pulley with a nut in it, pushing in and out an Acme rod. It's the same thing. Cleaning up the edges of the main plates. I decided to template these out, but in order to actually ensure that I'm drilling holes in actual straight lines, in order to make sure the wheels line up and it's not cocked over once it's on the rail, I have to clean up the edges so that it clamps square in the vise. Not the greatest work holding I've ever done though, clearly. Fortunately, that was a cosmetic error, so I just ignored it to be filed down later. The nice thing about all these 3mm pilot holes are that they're for a non-center drilling 5mm end mill, so if I don't get them exactly dead on, it doesn't really matter. It's literally just chip clearance. The end mill I actually tried to really line up with the template that I printed out though. Obviously, if you're using a harder material or smaller tooling, you should probably be more careful to maintain concentricity, since uneven loading on your cutting surfaces can cause deflection. I'm counterboring these M5 holes so that the low profile heads can seat below the surface of the plate, since the Z-axis bearing housing is going to sit right flush against that plate. I'm using slots instead of eccentric spacers. They're just easier to deal with, and since I have a surface plate, shouldn't be particularly difficult to set up. I found on a previous build that eccentric spacers are actually just difficult to get at and kind of inconvenient to use. So I'm going to try and avoid them on this project. Probably only going to use 2 of those 3 slots, but I wanted to drill all 3 just in case while I had this thing lined up in the vise. This is a spacer block. It sits between the 2 wheels at the top, keeps the 2 plates exactly the right distance apart for the wheels to turn freely and the 4020 V-slot extrusion to pass down the middle. That's the really nice thing about having a digital indicator. You can mix imperial and metric measurements in the same system. Obviously I have to take off the 100 thou for the edge finder radius, but then I'm actually working in metric, so I need to switch over. This is the top of the block. These 3 holes run vertically and will be tapped for M5. This is what will hold the actual main drive plate on and kind of tie the whole carriage together. Onto the V-wheel spacers. These are pretty straightforward, just 5.5mm thick with a little nub on the front to catch the inner race of the wheel bearings, just to give the wheels enough clearance not to rub on the side of the plates. They then get cut off at about 7mm. I just eyeballed it. 7mm thick so that I can clean up the backside and make sure it's perfectly parallel to the front side. Since if it's not parallel, then the wheel will get cocked over slightly under tension, and then it won't run exactly straight in the V-slot track. Rinse and repeat. I made 8 of these. If I needed 2 more to do that 3rd slot, then I could just knock them out real quick. Not a big deal. Since these are about 3/4 of an inch in diameter, and I don't have a 3/4 inch ER32 collet, and 7mm definitely isn't enough to catch in the 3-jaw, then I had to go over to the mill, hold them in the R8 3/4 inch collet, and turn them that way. It actually works okay, I've done it before. A mill is, after all, just a lathe turned on its side. The process here is a little convoluted, but it's fairly straightforward. I'm loading them on the 123 block because that block is flat to the 123 block in the vise, which is flat to the table. So I know that whatever I'm putting on that block is perfectly square to the spindle, which means that when I grab the spacer in the collet, I know it's exactly parallel to the sides. Other than that, I'm just cleaning up the parting face, making sure I'm getting an accurate measurement, and then taking off exactly what I measure to bring it down to 5.5mm. Simple. I generally got plus or minus 20 microns, which for this use case should be plenty sufficient. Okay, between the last scene and this scene, I installed the DRO. You'll probably notice the distinct lack of cuts and constant use of the digital indicator. I only have to zero once and then I can just bang through the whole thing. As long as I don't take the workpiece out of the vise, obviously. So that's the 3 mounting holes that we saw for the block in the previous clip, and the 2 pre-drills for the lead screw and the motor shaft. These are the 4 M3 clearance holes for the NEMA 17 motor mounting pattern. And then I'm going to take the 3/8 9.5mm end mill and drill clearances for the 3 8mm rods, the 2 linear shafts and the lead screw. They're all 8mm. Then I'll start the counter bore for the NEMA 17 motor shoulder. Using a boring head, starting concentric, just to try and get it out to a point where I can really use the head. It does remarkably well with these super cheap import carbide boring bars, which I ended up taking off the lathe because they don't really work very well for that. Once that's done, adjusting the head, releasing the gib screws, and then racking out the micrometer slide and tightening it back up again. Since this is just for the motor mount shoulder, I'm just eyeballing it. It's not super critical here. It's just a clearance hole. Once you've got some real clearance there and you're not taking super deep cuts, it gets really well behaved. A couple more passes to get it out to where it should be, and it looks something a little like this. Testing the motor, everything lines up. Seats flush, doesn't rock. Screw holes line up. You can see the bottom of the M3 threaded section there. Perfect. All of the plates and blocks that make up this carriage are basically the same. They all have a plane of symmetry, so I end up touching off all of them in basically the exact same way. First, I zero the axis across which they are symmetrical, and then on the DRO, there's a split function which effectively allows you to zero down the center line of an object. It's usually used for things like cylinders and circles. You sort of just about barely grab one side of it and then just barely grab the other side of it, and then it gives you a line down the middle of it. You can center up on a shaft to put in a keyway or something like that, or possibly find the center of a circle if you're careful enough. So as soon as you hit the half button and the axis that you want to split, then it immediately moves you zero plane to the center of the object. For the other axis, I just want to leave the zero plane at the top of the piece so that my zero lines form a sort of T. The thing with zeroing off from only one side is that you have to account for the thickness of the edge finder itself. Since this edge finder is 200 thousandths in diameter, I have to take off 100 thousandths, or the radius, the distance from the center of the spindle to the edge of the workpiece to get the true zero. And on this one, like on several other ones, I forgot to do that. Fortunately, I taught it fairly quickly, as you can see here. It was only after the first 2 spot drills where I noticed that my hole that was supposed to be 4mm in from the edge was more like 1.5 millimeters in from the edge, and the light bulb went off. So I just went back to 0, counted 100 thousandths in, re-zeroed, and then changed back to millimeters, and everything was fine. This is the reason why you'll often see Deichmann scribe line sort of sanity marks on workpieces, even where I'm using DRO or some other method of measurement where it can't really go wrong. It just keeps me on track and makes sure that my actual metrology is right as well. Usually a good plan, since when you're trying to keep track of a whole bunch of measurements at once and plan your next several steps and work holding and everything, it just keeps you on track without having extra sort of mental load. Onto the second side here, this first central hole is just clearance for the lead screw. This starting drill, I think, is about 9.8, 10 millimeters, somewhere on there. So I'm just going to leave it at that. The outer 2 are, of course, for the bearings. So they get enlarged to 14.5 millimeters, ready to get bored out to about 14.9 or so. If I recall rightly, the bearings are nominal 15 millimeters. I think they're about 14.96 or 7. somewhere on there. You can't inherently trust drilled holes to actually go perfectly vertically down, so I'm reseating the workpiece in the vise and really trying to make sure that it's set up perfectly vertical so that when I put in the bearings, they will also be perfectly vertical. That's the grind on the brazed carbide tip of the boring bar that I did. Knocked off the corner, and then a lot of back rake and side rake, trying to give it quite an aggressive positive grind as much as I can around the actual geometry of the boring bar. I did that on the diamond wheels that I use for TIG tungstens. Probably not the best idea in the world, but it should work okay as far as I'm aware. So far, regrinding brazed carbide tooling has actually worked pretty well for me, so I may end up just getting an actual diamond cup wheel so I can do it a little bit more accurately on the bench grinder. Lots of trial and error on getting the fitment with this one. I didn't want it to get really loose, so I was barely moving it, just a thousandth or so on the diameter each time. Then obviously once I had the right setting for the first side, then I could just directly duplicate that to the second side. Installing the bearings was pretty straightforward. A little tappy tap tap with a soft face mallet did most of the work. On the second side, it seemed like the boring head had been turning a slight taper because the hammer just wouldn't get them in all the way, and they wanted to kind of cock over as if they were riding an angled sidewall. But that's not much of a problem when you have up to 20 tons of hydraulic pressure. One of these days I'm actually going to build a proper set of dies and forms and stuff for that press. I always just have to make do with whatever's in the box of scraps. Onto the adapter bar. This wasn't originally part of the design, and I'm kind of disappointed that it had to be, but it's just kind of a physical reality based on the diameter of the secondary pulley, the one that actually transfers the motion from the belt from the stepper to the linear motion of the lead screw. Since that has to be a certain diameter in order to take the bearing in it, and the bearing has to be a certain size to be able to get attached to the mounting plate, etc, 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 it just ends up that's the diameter that the linear shafts have to be apart, and therefore there has to be an adapter plate because the laser housing itself just isn't big enough. I mean, it's not the end of the world, it's just a little bit clunky, and the original design was more elegant than that. So I was originally going to make all of the holes in the adapter plate 8mm, so that the rods, the two linear rods, and the lead screw would all just fit straight in and get grub screwed just as is. But then, in the interests of the whole perpendicularity, squareness, straightness endeavor, I decided to just stick with the 6.9mm of the stub drill, and therefore the ends of the rods where they fit in the holes obviously have to be turned down to 6.9mm. The collet chuck came out there because the shaft inside actually extends all the way to the back of the Morse taper section, and therefore I couldn't actually get the drawbar inside the threaded section. Just firming up the seating inside the Morse taper fixed that. I didn't have any more problems after that. These shafts were definitely through hardened. I tried to cut them on the bandsaw, but it's barely scratched the surface, so I had to use an angle grinder instead. Fortunately for the turning, the carbide inserts didn't have a problem. They were actually a lot happier with taking off the really tiny amounts that I was eking it in by as well. On unhardened materials, they don't like taking less than about 4 or 5 thou on a cut. One of the final major things was to add the mounting pattern for the Z-axis bearing seat. There wasn't really a way of clamping it on there while everything was together and the pulley was defining the distance and everything, so I kind of had to eyeball it. Ended up a little tight in the end, but it wasn't too bad. And then since the heads on the cap screws were so tall, in fact as tall as the actual thickness of the flange itself, I just counterbored for the Accu Security Torx M3s that I had for the NN14 build. In fact, you can see all of the screws that I'm using there. All the M3 tap screws are the monster bolts, as you can see right in the front of the surface plate there. The Accu Security Torx M3s I had in 6mm, they're what's in the bag to the side there, and then all of the M5s I'm using are open builds, as you can see in the bag at the back there. It's kind of difficult to really adequately describe everything that's going on here, because like everything you do on a surface plate, it's really heavily influenced by feel. In fact, only really scraping is done visually. Almost everything else is some form of rocking or like glancing action. Obviously, the overarching point here is to make sure the Z-axis linear shaft bearings are square and perpendicular to the axis through the two main wheels that form the, what will it be, the x-axis, maybe? Yeah, the x-axis of the gantry. Since that's going to be kind of locked in stone once it's fully assembled, and I really need to make sure that as the laser travels up and down, especially if it's a multi-pass cut, probably less so if it's sort of dialing in a focal length or something like that, some kind of calibration function. But if it specifically has to go over the exact same path multiple times, then ensuring it's traveling on a linear axis perfectly perpendicular to both X and Y is kind of critical. At least if you want the sides of your cuts to not be all melty and jagged and weird. So since I already basically determined that the bearings are perpendicular to the actual block that they're housed in, then all I really need to do here is make sure that the top of the block is perfectly coplanar with the two edges of the main plates, since they're where this top mount will be resting. Or even if not coplanar, then at least the two planes formed by the top of the block and the two edges are parallel between themselves. If all of that's together, then everything automatically lines up. Obviously, this plate doesn't actually have to be perfectly in any particular location, since all it's doing is holding non-critical parts. Just like on a machine, the only parts of the machine that are actually ground and scraped are the bits that things are sliding around on. All the bearings and lead screws and everything else kind of get to float wherever they need to float in order to provide proper mechanical clearance for reduced wear. I got a smaller, lower torque stepper motor for the Z-axis, I think between the reduction of the two pulleys and then the reduction inherent to the screw drive of the Z-axis. The lower torque shouldn't really be much of an issue. The idea is more just to keep the whole carriage assembly a little lighter weight and possibly balance it a little better. Even though it looks like there's a lot of mass up front, the copper and steel in the motor actually pushed the balance point back when I was using a regular size NEMA 17. Little tricky to get this part on. I guess I drilled that mounting pattern for the bearing flange a little far forward, but it wasn't too far off. I got there in the end. I figured out there was kind of a trick to it. If you partially but don't fully engage the grub screw on the D shaft of the motor and then put the axis bearing on first, then everything kind of just slips into place. There are actually a couple more things to do other than in this video. Just a couple holes to tap, a couple minor clearance slots to mill. Nothing that was interesting enough to warrant putting in this video. But yeah, that's the assembly and the finished product. I think it came out pretty well. I'll add the laser and the fan when I do the electronics. Okay, that's it. Here it is. More or less complete. Like I said, a couple last minor things to do, but this is basically it. Ready to move on to the next step, which will be the next video. Building the frame, the gantry and the XY frame, installing the motors, figuring out how I'm going to attach all the belts and everything, And then the final video will be installing Gerbil or flashing Gerbil to an Arduino, setting up all the drivers, all the electronics. I'll probably do generating G-code from vector files with Inkscape and sending that over. I think I'm going to use BCNC to do it. That's what I originally used, and I think that's still my favorite option right now. And then yeah, we'll go through some test cuts and that'll be it. So that's the last two remaining parts of the series. If you like the sound of that, then I guess subscribe. And yeah, that's it. Thanks for watching.